Hi, grade nines. This is the last video I'm doing for this section in terms of homework help. So this is similar to question 19. This is similar to the walking to the house. Okay, it's just instead of walking from house to house, you're just going from point A to point B on the river. Okay, so let's first read what it says. In Stillwater, Jana's motorboat cruises here. I clipped a picture of a motorboat. Cruises at 16.5 kilometers per hour. Let me help you out here because maybe it's not apparent to everybody, but still water, okay, still water means a lake, okay? And it means like we're talking about a lake, perfectly calm day, no waves. It's saying the travel, and there's no current, there's no nothing. It's just the motor doing the work. Okay, so in still water on a lake, calm day, no other variables, no other nothing. Jana's motorboat cruises at 16.5 kilometers per hour. On the river, however, and rivers are a different story, grade nines, the boat travels faster downstream than upstream because of the current. And this makes sense. So I've kind of driven a little diagram here, and I've said the direction of the current is like this direction. So when you're going this way, okay, this is called going downstream. All right. I feel I should explain all this because, we do have a lot of English language students at our school, and they may not get what the words downstream, upstream, still water mean. So downstream is with, there's the key word, is with the current. Okay. By the way, this is so similar to question 19. I'm not going to solve this whole problem for you, but I will definitely help you set it up. The key word there is it's with the current. Okay. Now, if you're going against the current, let's use this one. Okay, so on the other hand, if you're going against the current, that means you're going upstream. Okay? You're going upstream. All right? So upstream is against the current. So remember, rivers have current. It's kind of what makes rivers neat and kind of cool. It also makes rivers incredibly dangerous because if you get caught in a current, if it's a strong current, you could be in trouble. So in other words, let me put it to you this way. If your boat, whether it even has a motor or not, but if you're going downstream, the current is helping, okay? The current is helping you. It's pushing you. In fact, many canoeists and people with rafts, they don't have any, motors or anything like that, right? They just have maybe a paddle to steer. So, and you can paddle, of course, but I'm just saying, when you're with the current, you can let the current do the work for you. Upstream against the current, boy, you better have a motor or at least some paddles or some oars or something, because it is, well, the key word is against you. I guess I'll just write not. It's definitely not helping you. And trust me, I've been there in my years of fishing. Lordy, lordy, if your motor quits or cuts out, whew. Anyways, so let's just label this. Let's call this point A. And let me just use a different color for that just because I want to keep the color kind of neutral for the distance. So here's point A. This is where Jana's going to start, okay? And let's just say point B is over here, okay? This is where they're going to end, okay? So the first part, she's going down with the current, right? So she's going relatively fast. On the way back, she's kind of going, and I'm doing this deliberately, she's going relative because she's fighting the current, right? So yeah, she has a motor, but the motor can only do so much against the current, okay? So I'm just going to erase those two lines now. Okay, so this is the start. So the way you got to do this is you got to define, this is another distance equals a distance question. And you don't have to worry how far what is the distance between A and B? It's irrelevant. And I say that it doesn't matter. It's irrelevant because distance can be defined by speed times time. All right? Speed times time. I'm trying to make that a multiplication dot. Speed times time. So let's talk about this boat of Jana's going downstream, and let's talk about it going upstream. And we know the distance, she's going the exact same route. Yes, I know in real life that's impossible, but let's just assume it is possible. Exact same route. So on one hand, she's traveling at this speed, going down, and it takes her a certain amount of time. On the other hand, let's do the different color. Let's go back to here. On the other hand, she has a speed and a time. Actually, you know what? I'm going to switch. The downstream was I was kind of implying red, so I'm going to do red. Okay, just trying to be picky here on the last question. All right. So let's get that over here. So the distance, pardon me, the speed is equal to, and the time is equal to, okay. Now look, it says determine the speed of the current. Do we know the speed of the current? No, we don't. So do you want to use X again? I was going to use C for the current. Okay, so I'm going to use C just because X gets boring after a while. So let C equal the speed of the current. Okay, that's my unknown. I don't know how strong this current is. Some rivers, you know, they move, they go, and some rivers are like lazy and, you know, they're slow. So I don't know what the speed of the current is. However, I do know that her boat will go 16.5 kilometers per hour, and it's going to be helped by the speed of the current. So in other words, if the current was, let's say, 3.5, the total speed between the motor, right, between the motor and the current would be a total of 20, not 26, 20. Do you see that? So her motor contributes 16.5 kilometers per hour, and let's say the current was 3.5. I really have no idea if the current is 3.5. I just made that number up. I just know this fact, that her boat's motor is going to be helped by the current. Okay, and it says here, this is one easier part than, say, the walking question from question 19. It does tell you the actual time. It just says the boat takes 5 hours for the trip upstream. Makes sense. It's got to be slower. You're fighting the current. But it's only 2 hours to cover the downstream. Okay. So since distance is equal to speed times time, you could say the speed times time. Sorry. I forgot. My bad. That's supposed to be an unknown, Mr. Smith. You don't know if it's 3.5. I haven't done this question. I don't know if it's 3.5. It's 16.5 plus the current helper times 2. And yes, you can write your distributive properties backwards because I mentioned speed first and then time. So here's your speed and here's your time, right? And we're multiplying them. You've got to distribute, okay? All right, I'm just going to temporarily erase that just so I have enough room. Okay, times the time. Now, on the other hand, over here, let's talk about going upstream against the current. You're going against the current. So in this case, her boat can still, her motor is still the same power. It can go 16.5 kilometers per hour, but this time, isn't the current fighting her, right? Whatever the speed of the current is, it's going against the boat. Did you like that little demo there? And of course, naturally, this makes perfect sense. It takes her 5 hours. I was suggesting this current must be pretty strong. I hope the answer is a big number because otherwise I'll be a little frustrated. If it takes 3 hours more, that's a pretty strong river because usually, you know, powerful motor, whatever. So the distance here is equal to 16.5 again, but the current's not helping. It's hindering. It's working against you. And we're going to multiply that by the time. So again, I still did speed times time, right? And we're going to distribute the 5, right? But this time the expression looks a little different because on one hand, remember, all of these questions, grade 9s, it's like on one hand, on the other hand, connect. On one hand, on the other hand, relationship, connect, okay? So in total, what's going on here? In total, this is your setup. Oh, I can't believe how nice I am to you guys. Since the distance equals the distance, then we don't have to worry about the two D's. The D's are defined. The distances, since it's the exact same, she went the exact same route there and back. I'm not even going to try and draw another line because it's supposed to be the exact same route. You don't have to worry about it. You can just equate these two things. So for those of you who are picky, I'll write the distributive property in a more normal order. And we've got equals over here. 5 is equal to 16.5 minus, sorry, that 5 is looking a little whack. 16.5 minus C. And guess what? That's all you get. I'm not solving this for you. It's a double distributive property. Boom. Enjoy, grade 9s. Yeah, I know these word problems are challenging. Good. It's about time we stretched your brain. Yeah? I think so. Okay. Take it easy, everybody. Have a good one.